Hello, Tom. Your physics experiments are getting some attention. There's a lot of emails out there. People want to know a little more about what are they? What do they really mean? Can you give us a little more information?
Yes, I can. I think that's probably timely. I've talked about these before, given bits and pieces out, since I guess back in 2016 when these experiments were first presented in LA. And any of the listeners want to see that, you just go to YouTube and look for MBT-LA 2016, and that's when I first offered them. So if you want the really the in-depth description of these experiments, go there. But what I'd like to do today is just tell a little thumbnail sketch of what they're about, why we're doing them, what we hope will come of them, and so on. I'm getting a lot of email that's been asking me questions about these experiments, and it's not a subject that I can easily answer. It would take me hours and hours to actually type out with my two stubby little fingers an answer to each one of these questions. So I want to describe really what they are, what's going on, and kind of what we hope that we'll be able to do with them. And then at the end, I'll give you a little update on where we are in the process of getting them done. Okay, first off, the experiments that I'm doing are quantum mechanics experiments. They are variations on the double slit experiment. And that's a good experiment to do variations on. The double slit experiment was one that Richard Feynman made this comment about it. He said, if we understood how this double slit experiments worked, we would understand the mystery of quantum mechanics. Within this experiment, the knowledge of what's really going on, is there. We just don't understand it. And that's true. This experiment was actually the birthplace of quantum mechanics. It was this experiment that initiated quantum mechanics, because this experiment provided a result that was just not explainable with any of the physics we had at the time. So a new branch of physics was really created just to explain it. And of course, as it made its explanations, the field grew and grew, and hundreds and hundreds of other experiments were done, many of them just as strange as the double slit experiment. So I'll give you just a kind of a 2 or 3 minute sketch of the double slit and what it is and why that's so amazing, and this secret that it seems to hold. And that is, we know that if we send light, like from a flashlight or from a laser pointer, even better, if we have a laser pointer and we point it at two slits that are in a piece of cardboard, say, or something that would block the light. So we have this masking material, and we're going to put two tiny little slits in it. Very tiny little slits, narrow little slits. And if we shine this laser pointer and cover up both of those slits, we will get a diffraction pattern. That's because each slit serves as a source. Each source then puts out you can think of like a hemispherical wave. The wave comes out of each source and goes in every direction on the other side of the slit. Well, where those two slits have a difference of one wavelength to, say, a screen behind the slits, then the waves from each slit will reinforce each other, because there's just a one wavelength difference between the distance from slit A to this point on the screen and from slit B to this point on the screen. Just one wavelength difference between the two. So the waves reinforce each other and you'll get a spot of light there. And there's some places on this screen where the distance from slit A to this point on the screen and from slit B to this point on the screen are exactly a half wavelength different. And therefore the two waves will interfere with each other and you get no light at all. You get a dark spot. So you get what's called interference fringes, where the two waves from each slit interfere with each other. It's called a diffraction pattern. Okay, so that was an optics experiment with a laser pointer, say. And the laser pointer beam, little circle that the laser pointer makes covers up both slits. Okay, so the problem was that after Einstein discovered a photoelectric effect, we realized that light wasn't just a wave, but it also could be thought of as a particle, because the photoelectric effect told us that light comes in discrete little chunks of momenta. In other words, it's a particle. And these two views clashed with each other. It's a particle, it's a wave. How can it be both? So they did the double slit experiment, which was to send one particle of light at a time, and those particles were called photons. So one photon at a time toward these slits. And that was going to tell us something interesting, because would we get our same diffraction pattern like we did when we shined billions of photons all at the same time from our laser pointer? Or would we get, that's the wave pattern, or would we get a particle pattern where the particles would go through a slit and then hit the screen right behind the slit? So since light is light and particles are particles and waves are waves, we had two seemingly incompatible views of what light was. And this double slit experiment was going to sort that out for us. Well, they did that. They found a way to send one particle at a time between the two slits. And you'll just have to believe me that they made this apparatus such that a particle would go through one slit or the other. Okay, so particles come toward the slit. So don't worry about how they accomplished that. That's part of the setup. And actually, if you go look at my original talk from MBTLA 2016, it's all explained in there. But it's made such that one particle will go through one slit or the other. At least that's the result of what's done. Actually, a statistical thing, but that's the result. So if it's a particle, these little particles should pile up behind each slit, because that's what particles do. They travel in straight lines. Newton told us that, unless there's some outside force acting on them. And there was no outside force acting on them. Well, what they found is that if they put these particles through these two slits, the particle would go through the slit and then redistribute itself in a diffraction pattern. Some of the particles would move to the left and hit a point, and some would move to the right and hit a point, and then there were the points in between where there was no light at all. So you ended up with what's called fringes, or basically bands of light. And these were because of interference, just like with the laser pointer and the beam of light. That's how they distributed themselves. So particles would go through the slit, and with no force on them whatsoever to make them move anywhere, they would distribute themselves randomly on the screen, but such that when they were done and you sent like hundreds of thousands of points through, you could see you got an interference pattern. And the question was, what are they interfering with? They're not interfering with each other because only one particle is going through the slit at a time. So physicists started saying things that really sound kind of silly, but they didn't have any other way to explain it. They'd say things like, well, obviously, the particle is going through both slits at once and interfering with itself. Or they might say, the particle goes through one slit, but it seems to know where to go. It's got some information that tells it it needs to distribute itself in a diffraction pattern. Well, both of those sound like solutions that were made up because there wasn't anything else to say. They're both kind of far-fetched. Particles don't split apart in half and then interfere with themselves. Nonsense. Particles don't come with information that tells them where they need to go. They don't have little rocket motors on them that can make them go anywhere other than in a straight line, just like Newton said. So where did this force come from that makes them distribute themselves in this very particular pattern on the screen and not just pile up behind the slits? So this was the mystery that holds the key to understanding quantum mechanics. If you can understand how this works and why it works, then we will be much better off in our understanding. Quantum mechanics right now doesn't have that understanding. And this experiment was done in the very early 1900s, from about 1915 to maybe 1925. Over that decade is when most of this work was done. Okay, now at that time, the physicists were very excited about the fact that they had discovered something totally new about reality that they didn't know before. And this was a really big deal. But as time wore on and decade after decade went by, no physicist could come up with any idea of why it worked that way. Why would these particles, one at a time, distribute themselves in a diffraction pattern? Well, one of the things they did was they decided to see what that particle was doing when it went through the slit. So they would put detectors at each slit that detect the particle. Oh, a particle just went through slit A. Oh, a particle just went through slit B. Detectors gave them that information. And when they did that, the particles all piled up in little piles right behind the slit. There was no diffraction pattern. And then when they did not detect, they got a diffraction pattern. And when they did find out what slit they went through, then they got two piles. So it was a particle when you were watching, when you were taking data of which slit it went through. That's called the which way data. Which slit did it go through? So if you could get which way data, then the particles would act like particles. And if you didn't have any which way data, the particles would act like waves. So this is the experiment that kind of broke materialism, if you will. Material things don't act like that. Material things don't split in half and then interact with themselves. Material particles don't, spawn little rocket motors that make them, move themselves around on a screen to land someplace, not just any old place, but, someplace that's exactly the same pattern you'd get if there was a wave going through there, a wave pattern. So this is the big mystery in quantum mechanics. What is going on? Now, physicists early on freely admitted that they had no idea what's going on. They were clear about that. It was just mysterious. And that's why Feynman said that nobody, including himself, and he was one of the top quantum theorists, nobody really understands quantum mechanics, nor are they likely to ever understand quantum mechanics. The physicists decided that it would be a better thing, rather than to admit that decade after decade they just had no answers and weren't making any progress and they just had no idea. That was one thing they could say. That was true. The other thing they could say was, well, there is no answer. This question will never be answered. It's unanswerable. No one will ever know. It's one of those questions without an answer. Live with it. Deal with that. We're not going to get that answer. So that way, of course, they were no longer responsible. You're not responsible to produce an answer for something that has no answer. If it's impossible, then that gives you a good reason why you haven't made progress over the last 100 years, which has been about 100 years now. So that was the position that physicists took. It's not that we just aren't smart enough to figure this out. It's that it's an unanswerable question. Quantum mechanics is just weird science that will always remain weird. I found that to be a little hard to swallow. Okay, that's just my view of reality, says that we don't have things that just are weird science. This is a science like none other. All the rest of science is logical. All the rest of the science, you can look what's going on and understand the results of experiments. Quantum mechanics is weird science. You can't produce the answer just with logic. But they did find a way to systematically produce answers. And that was, they made an assumption that the particle really wasn't a particle. It was a probability distribution. And it had some probability to land at various places on this screen after it goes through the slits. And because of that probability distribution being the same as a diffraction pattern, then they ended up in diffraction pattern positions because that's the shape of the probability distribution. So they looked at all the possible places and looked at the probability, and at any one time, you don't know where it's going to land. It could land here or there or anywhere. And if you look at these little dots that occur every time a particle lands, they don't just start at one side, let's say the right, and then make a diffraction pattern. They just randomly hit someplace. But when they're all done, a diffraction pattern is there. So it just, each one hits looking like it's just a random placement, but a diffraction pattern is what comes out of all of them hitting, you see? So then another idea was that these little particles were intelligent. They knew where they were going. They somehow had the idea of where they wanted to hit, and they would go there. Well, that's pretty silly. That's probably even more silly than a particle splitting apart and interacting with itself. So we had intelligent particles, which is kind of a panpsychism in that everything's conscious, and these particles are conscious like everything else, and that means they have information and make choices, and they all decided where they were going to hit, such that all together, when millions of them hit, it looks just like a diffraction pattern. So not only do they have to be intelligent, but they have to be cooperative so they can all together create this pattern, you see. So that's the state of affairs that we have in physics today, in quantum physics today. That's kind of where we are, how we got there. So that was a little history. Hopefully that didn't take too long, but that's a little history of where we are. Now, in my work of trying to create a model of consciousness, based on my own research in consciousness, I came to the conclusion that the same rules that explain consciousness could explain this double slit experiment logically. Nothing magic had to happen. I mean, after all, saying that a particle splits apart and interacts with itself, or it's intelligent, or it somehow gets information and knows where to go, I would call that magical answers. If somebody says, well, how does this work? The physicist might as well say magic. Because what magic is something that happens. You know it happens, but you have no idea how or why. That's magic. So the magician saws the lady in half, but somehow at the end of the show, she's always put back together again. And if you don't know how, it's a very convincing trick. And you'd say, well, he's a magician. That's just magic. Well, we know there's a trick. There's some explanation of how that magician does that. But if we're ignorant of it, it just looks like magic. Well, that's the way this is. It looks like those particles are magic. And that somehow they seem to obey the rules of statistics with a very specific statistical distribution in mind, and that's the diffraction distribution. I don't like magic particles. I just didn't think that was a good idea. And since I was doing this conscious research, I saw a logical explanation. The logical explanation is that in a reality based on information, which my consciousness theory said this reality is information-based. So that another way of saying that is that it's a computed reality. And another way of saying that is that it's a virtual reality. These are all synonyms for the same thing. So calling it a virtual reality is saying it's an information-based reality. There are no particles. There are no waves. There's just information. Physicists are coming around to this. It was an idea that was kind of, only a few loners in physics had that idea. John Archibald Wheeler was one of them. Edward Fredkin was another. So there were a few scientists that thought our reality was information, because that's what quantum mechanics was telling us. But most physicists didn't know what to do with that. It's like, okay, yeah, so now where do we go? And nobody really knew what to do next. So in any case, a virtual reality has to be computed, and the computation can't be just random. Obviously, there's an intelligence behind the computation. There's something that organizes the rule set that defines the virtual reality. So that something is ordered. It's intelligent. You don't just make a virtual reality by randomness or without any intent behind it. Well, intent requires consciousness. Intent requires intelligence. So we have a virtual reality. There has to be some intelligent source behind the virtual reality. The information has to be computed somewhere. Well, in my model of consciousness, I also got a virtual reality, and the computer was consciousness. The consciousness is an information system. Part of that information can be arranged to be a computer. Part of it can be arranged to be individuated units of consciousness, entities that make choices, that get in information, make choices, and can then transmit that information to other pieces of consciousness. So that was my consciousness model, and in that model, a virtual reality could be computed from a set of initial conditions and a rule set. So that's how you make any virtual reality. We have virtual realities today like No Man's Sky, and they're made from initial conditions and a rule set. That's how you make virtual realities. So the neat thing about virtual realities are, and I'm going to skip a whole bunch of details here, but we're just going to skip across the things that you maybe need to know to understand what these experiments are about. One of the neat things about a virtual reality that's computed is that the reality only exists in the minds of the players. Okay, you have a virtual reality computer that computes the reality. You have to have players. A reality isn't just going to be computed for no reason, right? There has to be a purpose. Things don't just create themselves for no purpose. If they do, they're unstable and they disappear for no purpose, for no reason too. Things that are stable and very complex got that way for a reason. Okay, so if you have consciousness, the computer, and this consciousness computer is sending data to consciousness chunks called individuated units of consciousness who are receive data, interpret the data, make choices concerning the data, and then send information back to the computer that defines their choices, because their choices will change things in the data. Now you have a virtual reality, you see. So in this virtual reality, there is, let's say this virtual reality has trees and rocks and entities in it, okay? Entities could be elves or barbarians or humans like us or whatever. It could be like The Sims, it could be, like a fantasy game. But in any case, the virtual reality computer sends information to pieces of consciousness who interpret that information as the virtual reality. So the virtual reality only exists in the minds of the players. It's a multiplayer game. So the computer has to take all the changes, all the choices that the players make. I want my player to jump up and down. I want my player to run away. I want my player to stand on one foot, whatever. I want my player to go over and hit that other player. So these choices are made. The computer gets all those and computes the consequences, and then sends a picture back to the player that shows what the consequences were according to the rule set, right? It was evolved with the initial conditions and a rule set. So that's the virtual reality, and that's how it plays out. It's really a conversation between the players and the computer. There is no real reality. That's the virtual reality. It doesn't exist. It's only information given to players. Well, it occurred to me that that answered this issue in quantum mechanics. When you look, when there is somebody who's measuring the which way data, which slit did it go through, you get particles. And when there's nobody measuring the which way data and you have no idea, which slit it went through, you get a wave. You get a wave pattern. You get a diffraction pattern. So what is it about knowing that which way data that makes a difference between whether light is a particle or a wave? Well, it occurs to me that the looking at the data, the collecting the which way data, knowing which one it goes through, you now have a player. Okay? You now have a player who has information. And once that player has information, that's in the game. If he has information of a particle, then there's a particle in that game, and every other player has to see that particle too. But if there is no information in any of the players' data streams that they get, then there's really nothing that can be added to the virtual reality, because the virtual reality exists only in the minds of the players. So you see, if there is no information, there just is no particle. Okay? It's not there yet. If there is information, you do have a particle, and the particle will travel in a straight line and pile up behind the slit, like particles are supposed to do. Well, the system that is rendering this virtual reality has another problem, and that is, well, we send particles through, and the one that we can, when we look at the which way data, they pile up behind the slits. But when we don't look, the particle, we still send something through. It's going to go somewhere. Where is it going to go? Well, the system had a boundary value problem it had to solve. It doesn't want discontinuities in the reality. It doesn't want things that just don't add up in the reality. Well, light wave is just a bunch of particles. A light wave is a whole lot of particles that are headed toward those slits all at the same time. But the fact that there's lots of particles there doesn't mean a thing. Each particle has to act like a particle. But we know that waves make diffraction patterns. So when nobody's looking, and there's no information about which particle it goes through, in order to keep a discontinuity out of the virtual reality, the system arranges those particles that are entirely uncertain as to where they went in a diffraction pattern. So now it has solved the problem. It doesn't have a discontinuity in the reality. Particles, whether they're one at a time or a billion at a time, all act just the same. The difference is that if you look at one and say, it just went through this slit, now it becomes a particle at that slit because you've looked at it. It's information it had to send to some player, which puts it in the reality, and it can't do anything other than travel in a straight line and pile up behind the slit. If there is nobody looking at it, there is no data in this reality, it can't it can't act like a particle. Now it can act like a wave, and now you solve the boundary problem. You don't have this particle and wave duality, same thing, but it's two things. It's not the same thing. Well, these are the same thing, or it's not. Well, photons and light and waves and light, they're the same thing. So the system allowed the particles to distribute themselves in a diffraction pattern probability. So you look at diffraction pattern can also be a probability distribution. So it let it, distribute itself in a probability distribution that looks just like a diffraction pattern. So now light's consistent, particle or wave, works that way, it all works together. And scientists call that the principle of complementarity, something like that. That light was complementary to being both a wave and a particle. It depends on the experiment. If you look at it this way, it's a particle. You look at it that way, it's a wave. And they somehow decided it was both. And depending on the experiment, it would act one way or another. But there was no discontinuity, you see. One way you had to look, and when you looked, you created particles. The other way you didn't, and without looking, it acted like a wave. So when you're sending a beam of light from your laser pointer, you're not looking at each of the 100 billion photons that may be headed that direction toward the slit. You can't look at any of them, so you get diffraction pattern. Oh, see, the particles make diffraction patterns when nobody looks, and in a beam of light, nobody can look because there's billions of particles. So it's all consistent now. We have this consistent reality. Now, in my consciousness theory, I had come to the conclusion that the way the rendering machine puts new things into the simulation is by a process of looking at a probability distribution of the possibilities. That's the way everything comes in. So if you take your shovel and go out and dig a hole in the ground, and it's totally uncertain what's there. You're going to find a rock, you're going to find, a gold doubloon, that's, 800 years old. And what are you going to find down there? Well, when you dig that hole, because it's totally uncertain what might be there, there's a probability distribution of all the things that are likely to be there, and it takes a random draw from that probability distribution, which means the things are more likely is what you're more likely to find, and the things less likely you're less likely to find. But it takes a random draw from that probability distribution, and that's what you find. Because you see, in a simulation, there is nothing that is there. See, the reality doesn't exist. It only exists when the players get data streams. So what's under the ground, no players looked at that. There is no data stream. It's not defined in the reality. So that's how the system defines new things in the reality, from a random draw, from the probability distribution of the possibilities. And it does that in the macro world, whether you dig a hole or whether you, open up your refrigerator door and you have no real memory about what's in there because you've been away for 6 months. It doesn't matter. That's how it deals with this uncertainty. When we don't know what's there, it has to put something there, because when you pull that refrigerator door open, it has to render something. It can't be just a black hole in there that sucks everything in. That won't work. That's a discontinuity. Something has to be there. And because nobody has any idea what's there, it has to put something in there. It has to draw something in there. And what it draws is a random selection, or a random draw from the probability distribution of the possibilities. You see, that's the way that works. And that accounts for all sorts of things that happen in consciousness. That was my theory about consciousness. So with that theory, I can explain a lot of the artifacts of consciousness. Now, it also seemed to explain quantum mechanics. So I have some quantum mechanics experiments that I put up, and that's one of them. That's one of the simplest ones, just to look and see whether or not the collection of the which-way data is the thing that makes the difference. Okay, now, quantum mechanics has decided that it doesn't like that. It doesn't agree with that. It says that the particle somehow becomes entangled at the slit by going through the slit. And within that entanglement, it gets the information that it needs to do what it does. Yes, you viewers can't see Donna, but she's over there looking with a, like, really? Yes, that's I get that kind of reaction
Not
too.
a lot of logic there.
Yeah, okay. It's entanglement that gets that information of which slit it goes through. That information is not available to any user, to any player. It's just there. the system knows, and because it knows and it gets that information, then it knows what to do. Okay, so it's the entanglement is the key. From the consciousness viewpoint, it's a consciousness getting the information that brings that particle, that brings that potential particle, that brings that probability, that random draw from that probability distribution of the possibilities. A particle is drawn. Something has to be drawn there because, it looks at all the possibilities. What could be there? And the system is constrained in two ways. What they find there has to be consistent with the rule set and has to be consistent with history. Okay? It has to not be out of place in any way. In a time sense, in a historical sense, it can't be out of place. And in the rule set sense, it can't be out of place. If there's multiple possibilities, then there's a random draw to see which of these possibilities is what's actually going to be there. But whatever's there will be okay because we know it has to fit in the timeline and it also has to fit with the rule set. So it's not like it's going to do something that's, that is going to surprise everyone. It needs to be constrained in that way. Okay, so that's one difference between my viewpoint and quantum mechanics viewpoint. They get to a point where they have come to an understanding that entanglement is the mechanism that's used. And that is part of their theory. Now, it's possible that they're correct. I'm a scientist, so I believe very strongly, and you don't know the answer until the experiment is done. It's possible they're correct, but it's also possible they're not correct. And here's what I mean by that. In order for me to take my model of consciousness and extend it into explaining quantum mechanics, I have to make some assumptions. One of my assumptions is that the computer will find the most efficient way to run its virtual reality. It won't do it, with really inefficient code. It's going to do it the most efficient way possible. Now, if any of you are programmers, you know that if you give 10 programmers a very complex job to program, and each one of them is told, now do it as efficiently as possible, you'll get 10 different programs. They'll all work, but they'll be programmed differently. It's not like there's just one way to program a solution. Digital information systems are hugely flexible. There's a million ways to program anything. Okay? Choices have to be made. People decide, well, if I do it this way, okay, it makes this more efficient, but it makes that less efficient. So now you have to make a choice. Which way do you want to do it? And one programmer will pick one way, another programmer will do it his own, a different way. So there's lots of ways to skin the cat in making programs. I'm looking at the larger conscious system and saying, well, from the things I know about the system, from the things it's done before, how do I think it would have decided to make this virtual reality and the rules that govern its rendering? Well, there's different ways to do that. We've looked at computer games, and we see they're all done differently. The Sims is not just a recreation of World of Warcraft with monsters turned into things that look like people. It's done differently. And there's No Man's Sky is procedural programming, which is done very differently than either one of those other games. No Man's Sky is vastly more efficient. And one of the ways it works is it defines its reality only in the minds of the players, because that's just a more efficient way to make a virtual reality. You can make a lot more virtual reality for a lot less work in the computer and a lot less storage and so on, and a lot less programming if you do that sort of thing. So in any case, so I pick, well, I think it will define the virtual reality only to be in the minds of the players. it could do something less efficient if it had its own reasons of why it would accept that lesser efficiency to gain something else. And I may not really understand what that something else is that it might gain by letting some rule set take the function of entanglement. Now there is entanglement. Entanglement's a real thing. It's not that I'm quarreling with entanglement, but entanglement typically has some conservation law. You have a particle that creates two particles. You have some single thing that creates two things. Well, those two things have to conserve energy. They have to conserve momentum. They have to conserve spin. There's the things that they have to conserve. That's why one gets a spin up, the other gets a spin down, because the first one, was neutral, didn't have spin. Maybe it was some other sort of particle. So typically you do that. Now just saying that somehow entanglement creates this information and saves it and tells the particles what to do is, to me, not very satisfying explanation. It's more of that magic. Okay? But to the quantum theorists, it's good magic and they believe in it. Well, what I did to see if my interpretation was going to be right, I went through the quantum mechanics experiments, all of them that I could find, and I asked some people who were working physicists who had access to things that I didn't have access to, if they would search. And I came up with nothing. There was no experiment that clearly solved this issue. Indeed, was it entanglement, or do you have to have information given to an individual? So, without the ability to know for sure, because all theory, without an experiment to verify it, is conjecture. Nothing but conjecture. So, okay, we have this idea in quantum physics that entanglement is the thing that kind of gets that information. Well, I can't find an experiment to verify that. Doesn't necessarily mean it doesn't exist, but I couldn't find it, and 3 or 4 other physicists who searched couldn't find it either. So in my mind, the correct answer is, let's go do an experiment and find out.
You'd like to separate the belief from the science.
Exactly. Well, it's conjecture. If there is no experiment, all theory is conjecture. You can come up with a theory and say, well, I theorize that this will happen and that'll happen and all these things, and here's the reason why, la da 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 da. But if there's no experiment to verify it, it's conjecture. Theory doesn't create facts. Theory creates potential explanations. You see, experiments create facts. So here we don't have, well, I should say, I couldn't find any facts that said, did it work this way or that way? Now, it's possible that it'll work just like the quantum theorists say, and it won't be the information that's a key thing. It'll be this entanglement that's a key thing. But the whole explanation for this entanglement to me is a little airy, enough that I want to see the facts. I want to see an experiment, just because they say, oh, we don't have to do that experiment. Everybody knows how that works. Yeah, but it's just conjecture without an experiment. So I would agree that it's possible that the system is working some other way. I may not have made the right assumption of how the system is rendering quantum mechanics, quantum mechanical systems, okay? I know pretty well how the system is rendering stuff in consciousness because I've done a lot of research there. So I feel pretty confident about that. But now I'm taking consciousness and extending it into a field where it seems like there just isn't enough facts to know what the answer is. So I could be wrong. I don't know everything the system does, and I don't know why it does it. But I start with an assumption that it's going to try to be efficient and making it such that all the data is computed on the fly and given to the players and that the players contain the reality in their minds. The reality is virtual, doesn't really exist. It's in the minds of the players. That is efficient. So I could be wrong there. There's other choices it could make. It could make this, this particular application of entanglement part of the rule set. For some reason, it just thought that would be a clever thing to do. But that creates other problems. Now you're creating realities because machines have memory, or the system keeps its own memory that the players don't know anything about, which opens up another can of worms in terms of making a consistent virtual reality that's seamless for the players. So you see, I look at that and I say, well, okay, that's a possibility, but that's not my first choice for the way I think the system would work. My first choice is that our reality just exists in the minds of the players. And if that's the case, then some player has to get that information before you're going to get a particle to go through that slit and just hit on the screen right behind the slit. In other words, you get something that acts like a particle. Because things come into this reality like particles, making spots on screens, only because it's in some player's data stream. Okay, so that's kind of the difference. So quantum mechanics has solved this problem by postulating that it's some sort of an entanglement issue. And they're convinced that works. Well, a little bit about things working. Quantum mechanics is a very mature science in a way. It's been around for 100 years, and they're able to do magnificent calculations with it. Okay? And they have come up with certain ideas about how things work, and they're very good. So for me to disagree with a scientific discipline like quantum mechanics, puts me in the position of, if somebody were making book on how this would come out, I'd probably be the 1 in a million guess, and the quantum mechanics, that is this mature science that does all these calculations, would be the favorite, no doubt. But it's not about winning or losing for me. It's about finding out. It's about getting the information. So I have to do this experiment first to find out what the facts are, because I can't find any experiment that makes a fact out of it. It's just theory. And people tend to make theories, and after a while they begin to believe them. And just because it calculates right answers doesn't mean it's right theory. You see, this is something that physicists lose track of. They all know it at the beginning, but they kind of lose track of it, and they begin to believe that their theories are facts. And that is that mathematics is the logic of quantity. The mathematics they do is no doubt self-consistent. Any logic that's not self-consistent, you immediately throw it away. You reject it. Here's an example. Bossy is a cow. All cows can fly. Therefore, Bossy can fly. The logic is perfect. Nothing wrong with that logic. Anyone who understands logic would say that logic is unflawed. It has a statement, Bossy's a cow. It has an assumption, all cows can fly. And it comes to the correct conclusion that Bossy can fly. What's the problem with it? It's got a ridiculous conclusion. The problem is it has an assumption that is not a fact. It has assumption that doesn't square with what we see in the real world. So what about mathematics and physics? Physicists use mathematics to describe the world. Mathematics is a system of logic. As long as you're consistent, it'll chug right along and give you consistent answers. When you apply that mathematics and you apply that logic to the real world, you have to make assumptions, because that mathematics is not the real world. It's just the logic of quantity. And how you apply it to the real world requires assumptions of how that logic fits our experience of the real world. You see, how does it fit our measurements of the real world? How does it fit our experiments of the real world? Those are the facts. Well, here's an example of when scientists had the mathematics worked perfectly, got all the right answers, but the assumptions were just wrong. They didn't make any sense. You can have poor assumptions and still get right answers. It's not true that if you get a right answer, your assumptions must be true. That is not the way it works. You can have compensating errors, or you can just end up with something that is logical, but doesn't represent the real world. And an example of that, back when there was an argument about whether the Earth was the center of our solar system, indeed the center of the universe, it was shown that if you considered the sun the center of our solar system, things worked out well. But the belief in those days, the standard belief, the one that most people had, was that the Earth was the center and things revolved around the Earth. And that seemed to make sense because the sun went up and down and up and down, and it looked like it was going around the Earth. And so did the moon go around like it was around the Earth, and so did all the stars kind of rotate. And from a view from the Earth, it looked like Earth was the center of everything. Okay? And just to show that that was the right answer, people discovered the mathematics required to compute all the motions of the heavenly bodies with the Earth at the center. Now, they did that, the math worked, but it required what's called epicycles. There were these little epiorbits, if you like, or epicycles, where the sun and the moon and the stars and things had to do little loop-de-loops, They had to not just travel around in big arcs, but they had to go back, they had to go forwards and backwards and do all these little circles in order for the math to work out right. So they had a system of mathematics, was entirely consistent, nobody made any math mistakes, and they could compute all the places where the heavenly bodies were, where the planets were, where the stars were. They could compute it, and accurately. So if you say, well, they get the right answer, they must have the right theory. Wrong. There was no good reason why these things ought to be doing little circles and loop-de-loops and going back, going forwards and backwards. Just didn't make any sense. But the math said that was right. You see, so math can give you a right answer even though your assumptions are wrong. And quantum mechanics isn't any exception. Quantum mechanics has developed a mathematics that is good, and it's good at predicting the results of experiments. That doesn't mean that all of its assumptions are right. Now, it also doesn't mean that all of its assumptions are wrong. If all of its assumptions are wrong, it probably couldn't predict the right answer. But it's got some things right. My assumptions and its assumptions are exactly the same. That is, particles are probability distributions. Everything's a probability distribution that is completely uncertain. See, that's uncertain what's going to be in that hole that you dig. When things are it's uncertain what's in that refrigerator. When you have uncertainty, and rather complete uncertainty with these little tiny particles that nobody can see, you see, we don't know where they are. Well, with all that uncertainty, where are they, is going to come out of a random draw from a probability distribution of the possibilities. So I agree, and they agree. They say, okay, if we think that particles aren't particles, they're probability distributions, then we can compute right answers. So they got that assumption. It's a good one. I agree with them. But now we get down to this assumption about how the double slit works. Again, this is the key thing, just like Feynman said. If you understand this, you understand the whole thing. So now we get down to this, and they say, well, entanglement's how it works. See, here's the math. Da-da-da-da. See how good it works? And this math works really well on all sorts of things, so it must be true. Not the case. It's conjecture until there is an experiment that turns it into a fact. Well, as far as I know, there is no such experiment. It is not a fact. And it doesn't have to be right just because quantum mechanics gets a lot of right answers, you see? So that's the point. So it's not that I am crazy and think that, quantum mechanics, this mature science that's brilliant and thousands of physicists are crunching away on every day, How could I just say, well, they don't understand it, I understand it. I'm not even a quantum physicist. I'm an old guy. Most of the quantum physics that's been developed was developed after I got out of graduate school. You see, so I don't claim expertise, and that's why I know I'm a smarter expert than they are. I just find that the way I'm applying consciousness to quantum mechanics makes sense. It seems to be the simplest and most direct route for consciousness to use in its rendering of this virtual reality. And I know it must do this in a very efficient way. It's an intelligent system. It's been doing it a very long time. If it hasn't optimized its code by now, that would be odd. So I just want to know that this works or doesn't work. So where everybody else is content to just let it be that because quantum mechanics uses it and quantum mechanics works, that this must be a fact, I object and say, well, let's do the experiment. Maybe it is. Maybe entanglement is the answer. Maybe. Maybe not. Let's do the experiment and find out. So it's just that simple, you see. It's not a fact till the experiment's done.
Well, clearly these experiments need to be done. So Tom, can you tell us where are the experiments now?
Sure. Okay, so I've given you a good idea of why we're doing this. We're doing this because my theory has come to a point where it's kind of stuck. I need to know, does it do it this way or not? This is my first guess because it seems to be, to me, the most efficient. I could be wrong, but I won't know unless I do the experiment. So that's why I want to get this experiment done, because if it turns out that's not the case, then I'll know the system chose another way to run its virtual reality. There's probably thousands of ways to run a virtual reality. I'm guessing at which one is the one it would pick based on efficiency. So one of the reasons I'm doing this is because I'm stuck and can't go on with my theory being projected into quantum physics unless I can get this experiment done. So it's important to me. Okay, now it's important to quantum physics because they're running on an assumption. At least I call it assumption because I can't find any experiment that turns it into a fact. And that assumption is kind of hand-waving. Somehow, it just happens. It's one of those things. It's not a real strong case in my mind for the way the physicists describe it now. It's one of those weak cases, a weak case like particles split in two, go through both slits. Yeah, no, I don't accept that as an answer. Or particles have this intrinsic knowledge of where they need to go when nobody's looking. I don't accept that as an answer. You see, these aren't good answers to me. These are kind of like if you can't figure out anything else, you make something up. Well, that's the way this entanglement thing comes across to me. I have not yet found that entanglement explained in any other way than just stating it as a fact.
So quantum mechanics is relying on the math with the right answers, but for the wrong reasons.
Yes.
As you saw.
Yes. So what happens is even if it comes out the way they say, let's say it comes out that entanglement is the mechanism that's being used by the rendering engine of this virtual reality. Well, if that's the case, I would say they got the right answer for the wrong reason. Just like the people who did epicycles and all the squirrely things that were going around, they got the right answer, but they got it for the wrong reason. You see? So just the fact that it turns out that it is entanglement and not in the minds of the players, like I say, that just gives me another place to look. So my theory then goes on. But I can't go past this point till I settle this one thing, whether it's a fact or not. No sense going on until you kind of got to You got to do one fact at a time. That's how theories are made. So even if it turns out to be entanglement like the quantum theorists say, I'm thinking they got the right answer for the wrong reason. And why? Because just as Richard Feynman said, it's just weird science. It doesn't make sense. When they do the delayed erasers, there are physicists who say, well, obviously, since you do the eraser after the result's done, somebody has to go backwards in time to change that result. Nonsense. That's another one of these hand-waving things that you make up because you can't think of anything else. Nothing's going backwards in time to change things. You see, just like the particles that split in half and interfere with themselves, or the ones that somehow intrinsically know what to do. All of those, to me, are not convincing arguments. Well, they weren't convincing to Richard Feynman either. He looked at that and said, that stuff doesn't make any sense. Nobody understands why it works the way it does. Well, that means quantum mechanics has some things in it that are just unknown, that people don't realize. It's got some assumptions that are probably wrong. See, they've tried very hard to make quantum mechanics be as materialistic as possible. People who have beliefs and trying to make things fit their beliefs often tend to make up assumptions that make them feel good because it suits their belief, but that aren't right. So I will go on with my application of consciousness theory to physics because I know consciousness is fundamental. The physical is a virtual reality. It's secondary. It's computed. It's not fundamental. So I know there's a connection there, and if I guessed wrong about how this thing works, well, I'll refine my theory. I have to find this out first. So while I'm doing this one, I came up with a few other ones that would dramatically show that, one, this is a virtual reality because it would do something impossible. Just like the double slit does something that's impossible. Particles just move around and hit the screen in a diffraction pattern for no apparent reason. Okay? No material reason anyway. There is a reason, but that has to do with consciousness and probability. All right, well, I have some experiments that will do something like that, but even more dramatic, that they will do things that just are impossible. They will be able to predict how the direction in which a particle is spit out of a decaying atom. Impossible. They will be able to predict whether a particle will reflect or transmit when it hits a half-silvered mirror or a beam splitter. Absolutely impossible. So if those things work as well, then this will be a very dramatic set of experiments that may change a lot of minds, because not that they prove anything. Experiments don't prove anything. They lend evidence. They lend evidence because you do an experiment, you make a measurement, and you've got a fact. Facts add up to evidence. Facts aren't proof. Facts are evidence. You see, like bossy flying. We'll say, well, cows don't fly. Well, all of our facts say cows don't fly. Nobody's seen a cow fly, but who knows? We don't know the possibilities. But right now, that's a fact. But we won't say, it takes a little arrogance to say this is a law of nature and it'll never change, and what we know everything that can possibly be known about that. You have to be pretty arrogant to say that, because there's a lot of millions of years yet that people are going to figure things out, and we don't necessarily know everything. So
there were lots of times in history where people have made those statements and have gradually had to come along and accept some new thinking and a new worldview.
Always works that way. Newton had laws, and then when we found out that Newton only applied to a certain part of the world, then they weren't laws anymore. You see, they just became it applies to this subset of our reality. But you need other kinds of ideas that apply to the larger reality. So that's kind of where I am, what I'm doing. What the point is, I'd like to be able to, if these experiments work the way I think, it will make a very strong statement, very strong evidence for a couple of things. One, that this is a virtual reality. It's computed. It's the only way you can come up. It's the only way you can explain these results if they come out the way I say. The second thing is it will have some very strong evidence for consciousness is the computer. Because in these experiments, you change things and the way the experiment reacts changes to your change. So obviously it's not just a machine, it's a thinking machine. It's an aware machine. It knows what you're doing and can rearrange its result to keep the reality as consistent as possible. And that tends to indicate that consciousness is the computer, which fits a lot of other things. And once you know consciousness is the computer, then it's an easy, logical step to understand what the virtual reality is for, why we're here, and with a little elementary logic, you end up with love is the answer, which is really where I'd like to go because that has the potential for making a huge difference in not just science, but everywhere. We would like to live in a kinder, gentler world, and that's what's important, that we get to that answer. And I support that with my consciousness. And the way to get attention to that consciousness is to do better physics. That's why I'm, taking my consciousness theory and trying to move it into physics, because I know consciousness is fundamental and the virtual reality is not. So anyway, this is where we're going. A lot of physicists now have come around to this is an information-based reality. Thousands, tens of thousands of scientists now think that's a good idea because that's what their experiments keep telling them. So I'm just stuck on this one little idea about how this virtual reality is rendered, and I need an experiment to get me unstuck. So, and I'll get unstuck either way. If it turns out that it's entanglement, that'll unstick me because now I have a better idea of how the system has made choices in its rendering. If it turns out that I'm right, that it's not entanglement, that it has to do with information, then that'll verify that the guess I made was a good one. So, see, I don't really see it as a win-lose. I see it as a win-win. Anyway, the experiment comes out, I get the information and get to move forward. So this is not really about me trying to tell the quantum physicists that they're wrong. This is about me trying to understand a particular point of quantum physics and find out what the facts are. Because right now it seems to me all we have is theory. And the theory is not all that convincing. And where theory isn't convincing tells me, because I see theories that aren't convincing a lot all over physics, and typically a theory that's just not all that convincing got that way because it made the whole system seem more materialistic, so it's a conclusion that's easy to jump to if you're a materialist. Now, whether that's the case here or not, I don't know. But once these experiments get done, I will know. And so will the other scientists. So this is a good experiment, period. It's not just a good experiment for me and my consciousness work. It's a good experiment. The physicists need this experiment too. If it works the way they say, well, they'll have now some evidence that their way is, was a good choice. They've made good choices, good assumptions. So it's exciting. I'm looking forward to it. And where we are now is that all the experiments have been written up in a thing called an RFI, Request for Information. Request for Information is kind of a light version of an RFP, which is a request for a proposal. In a request for a proposal, you send somebody a request, ask them to make a proposal. And they have to come back and say, here's what I would do, here's how much it costs, here's how long it would take. And there's a lot of work involved in sending back a proposal. So I didn't want people to have to do that much work up front because I know I'm trying to push a rock uphill. I got a couple of things biased against me. One, science doesn't like new ideas that are strange. It doesn't like new ideas out on the fringe. Even though we know from Thomas Kuhn's book that the big ideas always come from the fringe, but still people don't like fringe stuff because if it doesn't work out, then it makes them look silly. So they avoid fringe stuff, and also they don't like the idea that in my RFI, I have the word consciousness and I have the word quantum mechanics in the same paragraph. They think consciousness doesn't belong in physics, goes somewhere else, and if it has something to do with consciousness, then they don't really want to touch it. So I have a little bit of a negative bias that I got to work against to find physicists that'll do this. But I am going to find physicists that'll do it. I've sent this RFI out to probably a couple of dozen individual physicists and some institutions. So far, we've got no thank you. Mostly we get, I'm already busy. I've got all the work on my plate that I can stand to do, which is really what I expected most, because that's true. Physicists aren't sitting around just waiting for me, to give them an RFI so they can make a proposal. Mostly, they have their own grants. They have their own work. They're busy with it. They can't just take on another project. So it has to bump into a physicist who's willing to do some fringe science and who has just finished up a project and has some open space for a new one. Well, that's going to take a while to send these things out. We don't want to just send out, like 1,000 of them at once. That would just create chaos. So we're sending them out selectively. We're selecting our physicists for people who have experience in this area and so on. And we're sending them out to institutions who have instant credibility. So we're working at the top down, and then we're waiting for replies before we send too many more out, because you don't want to send out a whole lot of them if you've already got somebody to do it. So it's a slow process. So I would caution everybody to be patient. This may take the best part of a year. Right now, we've had the money in hand for 4 months, 4.5 months. We got it at the end of June, halfway through July, something like that, before it actually transferred to us. Everybody got their fees and everything out of it, and all the dust settled. So, we've had middle of July to August, September, October, November. It's about 4 months.
That's not much time.
That's not a whole lot of time.
For one of these things.
Yeah, it took us the first few months just to put together this little RFI, because it needed to be concise and very tight, because you hand somebody 20 pages and they're not going to read it. They're only going to look at the front. And we had a lot of other things to do. We had 3,000 or 4,000, what did we call them, rewards to fulfill. Remember, we got our money from a Kickstart, and in order to induce people to give, there was all sorts of rewards. The typical T-shirt and mug were there, but so were a whole lot of other things. All of these rewards have to be manufactured, have to be designed first, then have to be manufactured, then have to be mailed out, and it all has to be done in the most efficient and cost-effective way. So just doing the logistics of mailing out thousands of things takes some thinking. How are you going to do this in a way that preserves as much money as possible for the experiments, you see? So we're not just jumping into it and suddenly going down to the store and buying T-shirts. We had to think. I put together a nonprofit corporation called CUSAC, C-U-S-A-C, CUSAC, Center for the Unification of Science and Consciousness. It's a nonprofit. That had to be gotten together. There's a lot of work in putting together a nonprofit, and I have lawyers working on that. And I've just chosen a board of directors, which is part of the process that you have to do, and they have to be independent, so that's not just something you control. And anyway, all of this takes work. So we've got the corporation coming along, nonprofit. I wanted that so that the nonprofit could control all of the money. So the money goes into the nonprofit. Every dime of it goes into the nonprofit. Nonprofits, by law, have to be very transparent about what they do with their money, because they're getting tax-exempt status. People can give to it, take that off their taxes, And the government wants to know that if it's a tax-exempt thing, that it really is going to make the world a better place. It's something valuable, you see. So exactly what you do with your money and why you do it is scrutinized, and it has to be very transparent. So that was just a no-brainer. Let's make a nonprofit, put all the money in there. Now all the accounting procedures and all the ways of doing things are all defined by law, and that's what we'll do. So that makes it to where it has to be transparent and every dime accounted for. So that takes time. All the rewards and the logistics takes time. Coming up with the RFI and deciding who we want to send it to, that takes time. We're about 4 months in. All of our help, everybody that works with me, everybody that is involved in any way with what I do, except for the lawyers, they don't work for free. Everybody else works for free. So it's a bunch of volunteers. Well, volunteers have lives. They have jobs they have to go to every day. You know, they have families they have to take care of. And on the side, they're kind enough to volunteer doing this work for me, for CUSAC, you know, and so on. So you're one of those volunteers, Donna. You know, you and Keith do all the organization, plan all the things, put in thousands of hours, and you don't get paid a dime for it. So that's how this organization is being run. And I like that because as long as it's volunteers, you have people who care, people who want to be doing it. That is much better.
Well, that's
and it
what
saves the money. I want all that money for my experiments because I don't know
Yes.
how much they're going to cost. I have no idea yet until we get proposals back of what the costs are going to be. So I want to keep our expenses minimized. So we have an all-volunteer force, but when you have an all-volunteer source, folks, you need to be patient because you don't have a dozen people working on this full-time. You have a half a dozen people working on this part-time when they can. So we're moving along. I think we've got a tremendous amount of work done in the 4 months we've had to do it. I think sometime this year, or next year, sometime in 2019, we're going to get some experiments done. We're looking at multiple ways of doing it. We're starting at the top, working down. We've got another project that's starting at the bottom, working up. And that is, don't do it in a university with credibility. Do it in a garage or someplace else. Get the answers. Use those to leverage the university. So we're working at it from both ends. Anything that works, we're going to try to do. We've only got a certain pot of money to do it with, so we're going to be careful. And it's going to take time. So we're doing a lot in a very short amount of time, but I can't promise you when the experiments will actually be completed. I think it'll probably be in sometime in 2019. That's this coming year. And
Okay.
hopefully it'll be sooner, and hopefully it'll be, you know, some high-profile physicists with great reputations from wonderful universities with good reputations, because then, if it's done that way, then it's accepted immediately.
Well, there are several good physicists interested in consciousness, and the way you explained today at the beginning of our interview here should excite any physicist who wants to support the idea that this may be a virtual reality. And virtual reality means, when you said love is the answer, it means cooperation, the things that you're getting from the
Right.
people who are volunteering towards this. And that's the kind of love that you mean.
Yeah.
We have a purpose.
Right,
This is much better than a
To-
dead-end materialist viewpoint.
right.
So what you're going for, what these experiments mean, are a lot to humanity. So I
Yes.
thank you for that.
Sooner or later, we will get there. Whether we get there in this first round of experiments, that would be wonderful, but we'll get there one way or another anyway. This
Thank you,
round,
Tom.
the next round, or the round after that, we'll keep working on it until we understand that link between consciousness and physics, because consciousness is fundamental. Physics is a subset. Physics needs to be derivable from consciousness. I think I know how that might be done, but I have to guess at some things because the larger consciousness system doesn't tell me everything it's doing and why it's doing it. I have to figure that out on my own.
Well, you know your physics, and you're certainly an expert in consciousness. And when that idea comes together, we should have some interesting results and a better world.
Yeah. And I should say, all of these results are going to be very transparent. You know, like I say, for me, the results are win-win, however they go. It's going to turn something now that is just hand-waving conjecture into a fact. After that, everybody can take the next step forward. Until you get the fact, we're all kind of stuck. They're stuck happy with the assumption they have, and you know, I'm stuck that I don't know whether the assumption I made is right or not until I get the facts. So yes, we're going to move ahead with this just as quickly as we can.
This explains a lot to me why the quantum mechanics people are outraged that their math works, but they don't understand that the logic doesn't work, or that the reasoning doesn't work.
Well, yes, you know, quantum mechanics has this thing. They do math. You know, that's what Richard Feynman said. Shut up and calculate. You know, Christ said, but Richard, how does this work? Shut up and calculate. I can't explain to you how it works, but I know that if you do the math like this, you'll get the right answer. But getting the right answer doesn't mean that you have the right understanding. In fact, Richard Feynman says, we don't have any idea, we don't have any understanding, much less the right one, but we've got the right math that works. But the fact that the math works doesn't mean that all of its assumptions are right. Math has to be interpreted into the physical world. It doesn't just automatically represent the physical world. You got to take the math and say, here's how the math can be interpreted to mean physical things. But all of that's assumption-based, and math and the physical world are two different things.
So Richard Feynman knew
that
the math was getting answers, but he knew that there was still a mystery to be solved.
Right. And that's an interesting thing, because Richard Feynman was one of the best big quantum theorists.
I don't think anybody will argue with that.
You know, quantum theorists at the very top. But today you talk with the quantum folks that aren't anywhere near the caliber of Richard Feynman, and they are certain that they have the right answers, that all the assumptions are right, and there are no problems, even though
Richard Feynman wasn't certain.
Yeah, he wasn't certain.
Yeah.
But you read, I mean, physicists, you wouldn't think physicists would say these things, but particles split apart and go through both slits and interfere with themselves. Come on. That's not a good explanation. That's a desperate explanation. That's not really a good explanation.
Feynman wouldn't come up with that conclusion.
No, he wouldn't say that.
No.
He'd say, we don't know. He would never say that. And you have physicists have things going backwards in time, and they say, see, what's the other favorite thing? They split apart, or they don't split apart. They don't split apart and interfere with each other. They just interfere with itself. You got one thing, and somehow magic happens, and it interferes with itself. Well, that's not right either. Okay, these things are just metaphors. I'll give them that. At least the physicists that are a little more knowledgeable probably don't believe that any of that happens, just like Richard Feynman, but that they're somehow metaphors that people use. But basing your calculations on metaphors that don't really make a lot of sense, because that's what your math is doing. Your math is showing that these particles interfere with themselves, things like that. And they say, well, we just don't know how to interpret that because it's just weird science. You see, what I see is uncertainty. I see that there is room for better understanding. And if the way I'm approaching it is that better understanding, wow, that would be really good. But if it isn't, I'm going to continue to work on it. So yes, the big guns at the top, they were all very excited. And then the ones that came later, like Richard Feynman, they said, we have no idea why this works, but it does. Well, if you have no idea how it works, you're missing something. It's a science. It is logical. You just don't understand how it's logical. But it will become a logical science, just like any other science, once you have the right perspective in which to see it. That perspective, I think, is virtual reality. That's the perspective from which you'll be able to see it. Now, whether I've done it right or not yet, I don't know. But that will be the answer, I think. So that's what I'm working. So that kind of sums it up. What we're doing, why we're doing it, why quantum mechanics could possibly be wrong in something because it's this wonderful science that always works. It's really just a computational science now. You do the math, you get an answer. It doesn't mean that your assumptions are right. Just like it doesn't mean that the moon and the sun and everything else is doing little loop-de-loops in space. Yes, that's math works, but it isn't the way the world works. Math working and the world working are two separate things altogether. So that's kind of the logic for who we are, where we are, what we're doing, and the status of where it is. So it's kind of a little summary. So let's go do these experiments, find somebody that'll do them, and find out what the facts are.
I think this will create a lot more interest than perhaps we've had. Your explanation was excellent. Thanks, Tom.
You're welcome.